Hey everyone, today we're diving into a fascinating tech showdown that's reshaping the world of computing, ARM versus RISC-V. Both of these technologies are based on RISC or RISC, Reduced Instruction Set Computing, which differs from the Complex Instruction Set Computing or CISC architecture used by Intel and AMD in their x86 products. Traditionally, desktop and notebook computers use the x86 chips, although Apple switched things up with their M-series devices, which are custom ARM chips, and more recently, Microsoft revisited ARM processors with some Snapdragon X laptops. The main focus of this video is the two RISC processor architectures battling it out behind the scenes in almost every device you use, from your smartphone to your smart fridge. Let's explore how they began, what makes them different, and where this competition is headed. Believe it or not, ARM started in 1990 in a converted turkey barn in the UK. 12 engineers from Acorn Computers, Apple, and VLSI Technology formed Advanced RISC Machines with a revolutionary idea. Instead of manufacturing chips, they'd license the designs to others. The big breakthrough came in 1997 when the Nokia 6110, the first ARM-powered mobile phones, hit the market. Remember those indestructible Nokia phones? That was ARM's coming out party. By 2003, 1 billion ARM chips had shipped worldwide. ARM created specialized processor families for different needs. Cortex-A for high-performance devices like smartphones, Cortex-R for real-time systems, and Cortex-M for microcontrollers and low-power devices. Fast forward to today, over 250 billion ARM chips have shipped, and about 70% of humans interact with ARM technology daily. Talk about a success story. While ARM was conquering the commercial world, RISC-V was brewing in the hills of academia. In 2010, researchers at UC Berkeley in the United States created RISC-V with a radically different approach. They made it open source. The name tells you a lot. RISC stands for Reduced Instruction Computing Set, as we said, and the V represents the fifth generation of RISC designs that Berkeley had developed. Unlike ARM, RISC-V wasn't built for profit, it was built for freedom and innovation. The first real RISC-V chip, Raven 1, was created in 2011. By 2015, NVIDIA started using RISC-V cores in their GPUs, a huge vote of confidence from a major industry player. Today, giants like Google, Qualcomm, and Samsung are all exploring RISC-V, showing just how much momentum this newcomer has gained. Both ARM and RISC-V follow RISC principles. They're designed to do simple instructions very efficiently. This makes them perfect for mobile and embedded systems where power consumption matters. ARM has evolved through continuous commercial refinement. Think of it as a finely tuned sports car, optimized through decades of real-world testing and backed by hefty R&D budgets. RISC-V took a different path. It's like a modular vehicle where you can swap out or add components as needed. It consists of a mandatory base instruction set with optional extensions. Need specialized AI instructions? Add them. Want cryptography acceleration? Plug it in. This flexibility is RISC-V's superpower. The biggest difference isn't technical, it's philosophical. ARM charges both upfront license fees and ongoing royalties for each chip. This model has funded ARM's incredible growth but creates barriers for smaller players. RISC-V, being open source, charges nothing. Zero licensing fees, zero royalties. Anyone can design and manufacture RISC-V processors without paying a controlling entity. The standard is maintained by RISC-V International, a non-profit organization that ensures the architecture evolves in an open, collaborative way. ARM's biggest advantage is its mature ecosystem. We're talking development tools, operating system support, and millions of engineers who know how to work with it. This reduces time to market and development risk. ARM also has a proven track record. The designs deliver excellent performance per watt across diverse applications, crucial for mobile and battery-powered devices. Despite being proprietary, ARM offers flexible licensing options. Companies can license cores directly, design custom cores using ARM instruction set, or access specific combination of ARM IP. RISC-V's most obvious benefit is cost. No licensing fees or royalties mean significant savings, especially for high-volume products or startups with tight budgets. But it's not just about money. RISC-V's modular architecture allows unprecedented customization. You can add custom instructions and hardware accelerators tailored to specific applications. perfect for specialized fields like AI or cryptography. There's also the sovereignty factor. Using RISC-V means no vendor lock-in and complete control over your processor implementations. This independence might be increasingly important in today's geopolitically complex tech landscape. Finally, RISC-V's clean slate design can offer power efficiency advantages. By implementing only what you need, you can create smaller, more energy-efficient designs. RISC-V is gaining momentum fast. If current trends continue, it could challenge ARM in certain segments within the next few years. The shift is driven by a reassessment of the value proposition offered by proprietary architectures. The collaborative development model of RISC-V facilitates shared solutions and cost-effective experimentation. This could accelerate innovation across the semiconductor industry and revitalize chip manufacturing in regions like Europe. Currently, ARM maintains a performance advantage. The best RISC-V cores are roughly comparable to ARM designs from a few generations ago, but this gap is narrowing with each new implementation. The competition between ARM and RISC-V is driving innovation on both sides. ARM is introducing more flexible licensing options and enhancing performance, while RISC-V's open development model enables parallel innovation from multiple organizations. In the end, both architectures will likely coexist in a complex ecosystem, each finding applications where their strengths make the most sense. RISC-V is positioned to gain fastest in emerging applications and specialized domains. Think of IoT endpoints, industrial control systems, automotive microcontrollers, and custom AI accelerators. Academic research and education is another area where RISC-V will thrive. ARM will probably maintain dominance in established markets like smartphones and tablets, where software compatibility and time to market are crucial. What's certain is that this competition will drive innovation, hopefully leading to more efficient, powerful, and specialized computing solutions for all of us. So that's another one in the can. If you find this video interesting or informative, please consider liking and subscribing. And remember, be excellent to each other.